Curvature is pretty straightforward. I mean, the derivation of the curvature model is anything but straightforward. It's actually a fairly lengthy process, and fun is a relative term, you know, depending on what you find to be fun. Some people, and I don't argue this, would look at the curvature concept and say this is not fun, right? In terms of deriving the formula, other people are fascinated by it, right? Curvature itself, we call it, it's really just, if you simplify it down to just like a one single word to describe it, bendiness, the bendiness of a function at a given point. We could also come up with a bendiness number for any point along a curve. Right? That gives us the curvature. Right? So we can develop, kind of like what we did on a previous page with the unit tangent vector, we can develop truths, you know, relationships that we know exist based on past experience. So, for example, I know that a line is not going to be curvy at all. So its bendiness number, its curvature is going to be 0. There's no curve to it, right? But I know that a circle is going to have some bendiness number. I don't know what it is. I mean, I do, but in your position, I don't know what it is. But I know it's got to be something significant because it's a circle. It's like the definition of a curve, you know, of being curvy. So you kind of have those truths, those things that you kind of know intuitively. Right? What we want to do is develop a relationship that's going to help us to figure this out kind of on a global scale. Right? But you can see the shortcut formula, that kappa. I make my kappa a little bit differently. But you can see it's the derivative of the unit tangent vector divided by magnitude, divided by the magnitude of the derivative of your vector value function, right? So there's a lot going on here, and number 11 is probably not the place to start for it, although it's really not that bad. I'll come back to it though, because it's at a point. When it's at a point, it's a lot easier to handle than when you do it generally. It's just it's still not a pretty sight. So let's actually go to the problem on the next page, number 12, which kind of supports what I'm talking about. Curvature of a circle with radius a in R2. So R of t would be equal to a cosine t, a sine of t. And if we do this right, we'll come up with a relationship that'll tell us the curviness number or the bendiness number, the curvature, for any circle. Because all you'd have to do is come up with a radius and you'd be good to go. All right. So we already know what the unit tangent vector is, but you know, you can reinvent the wheel if you want. T of t, and I also need my that just glitched on me hard. We'll also need r prime of t anyway. So let me just chuck that in here real quick. Negative a sine t, a cosine t. So t of t, we figured this out on the previous or 2 pages ago, but also even if we didn't, we could figure it out anyway, just by dividing by the magnitude, r prime of t's magnitude, which is just a. So you get negative sine of t, cosine of t. So then t prime of t, that's the derivative of each of these two components. Derivative of negative sine is negative cosine. Derivative of cosine is negative sine. So then I just need some magnitudes and I'm good to go. All right. So I'll just kind of chuck that off on the side here. The magnitude of r prime of t, again, asked and answered. We already figured that out, but even if we didn't, it wouldn't take too long to come up with that result. It's going to be a value of a. The magnitude of t prime of t, that's what I was talking about before. If your vector valued function is made up entirely of sines and cosines, whether it's positive or negative, you square them, you add them together, you're going to get a 1. Square root of 1 is 1. All right. So then we have all the ingredients, and if you look at the rule here, you see it's just you're taking the magnitude of the derivative of the unit tangent vector and dividing it by the magnitude of the derivative of the vector itself. And that'll give you kappa, which I make like this. Just want a funky K, that's all. Right? So we're taking this guy, dividing it by this guy. In which case you get kappa equal to 1 over a. All right. So the reciprocal of the radius of a circle is the curvature of that circle, or the bendiness number. All right. So it's an inverse relationship. If you really think about it, let's say you have a circle with a really, really small radius versus a circle with a really, really large radius. Okay. So I just kind of look at it like you're walking along the equator, if you could walk along the equator. Do you feel like you're walking along a curve? No, you feel like you're walking on a straight line. Not very curvy at all. Right? So let's say, oh, what is the radius of the Earth? 17,000? Something like that. Well, let's say it is. I can't remember off the top of my head. So the curviness or the curvature or the bendiness number would be for a circle with a radius of 17,000 miles would be 0.000 up 17. Oh, geez, feet? I don't even know anymore. It's got to be miles, right? I don't know. Alexa, what is the radius of the Earth? 3,959 miles. I wasn't even close. I think you said 59. All right, well, anyway, the radius of the Earth, very, very large, would give us a bendiness number. Well, this is in terms of miles, so we'd have to be careful about units, of 0.000253, right? As opposed to a circle, let's say with a radius of 1 mile. Which would have a bend, I don't even have to put that in, a bendiness number of 1, right? So the larger the number, the bendier the curve is. So comparative, it's kind of like standard deviation. It's a comparative value. Is 1 a big number? Well, compared to 0.000253 it is. But is it in and of itself a big number? Well, I would still be thinking of a circle with a radius of 1 mile as not being very, very bendy, right? As opposed to a circle with a radius of, let's say 1 inch, right? Really tiny circle, right? Very, very bendy, right? All the way around, right? So it becomes a matter of perspective. Yeah, so the next one's along the same lines. We've tackled a lot of these problems already in terms of figuring out the magnitude and the derivative and the unit tangent vector. So there's a lot of kind of overlap here. But what I'll do is I'll just hop on down to number 14, curvature of any straight line in R3. All right, so for that one, it's kind of tricky because we need to generalize a straight line in R3. Each component needs to be linear, and it should be a vector value function, R of t. Each component should be of the form mx plus b, but we have a model that we use for this. Okay, we talked about it a while ago. See if I can find it easily. No, it was actually before that. Oh, yeah, here it is. These babies. All right, the vector form of a linear equation. And so we already have a way of representing this. X sub O, T, A, B, and C, Y sub O, Z sub O, etc. So I could just do a copy paste job here because these are vector value functions. But the interesting thing was we were working with vector value functions before I even uttered the term for the first time, vector value function. All right. So let me just and look at that. So I make my vector brackets the same every time, almost. All right. So that would be a straight line in R3. So I need the magnitude of that. Well, let me not jump the gun here. Let me find the derivative first. I mean, I could have just plugged it in, but I don't want to go too crazy. It's going to be A, B, and C because X sub O, Y sub O, Z sub O are all constant values. And AT or TA, AB, I'm sorry, BT and CT, that's a constant multiplier of the variable T. So derivative would just be A, B, C. Now that magnitude, really not much you can do with that, which is the double-edged sword because since we can't do anything with it, it means we're stuck with all of that. All right, but it doesn't mean it's going to be difficult. A squared plus B squared plus C squared under a radical, poor quality radical. And I lost my power of 2 for the C for some reason, slash, I don't think I ever wrote it in. All right, so my T of T is the ratio of these two jammies. I'm just going to do a little copy pasting. The story of this semester, right? It's just like write something, copy paste it like 300 times. We're dividing each of A, B, and C by corresponding magnitude. Get some commas in there, beep, and beep. Pop in the A, the B, and the C. Now, your reaction might be, dang, I got to take the derivative of this. But then if you look closely enough, you realize hopefully there's no T's. On the right-hand side, there's no T's whatsoever. That's great. That means everything's constant. So T prime of T is going to be the 0 vector. And the magnitude of T prime of T, the magnitude of the 0 vector is equal to 0. So when I want to find kappa, my curvature number, my bendiness number, it's going to be 0 divided by the magnitude of all of this stuff. I got to move that a little bit. So 0 over all of that, which gives me a kappa value equal to 0. All right, so not too bad once you get over the hump. All right. And a lot of it has to do with just the thinking steps. Because once you recognize, oh, it's constant, derivative of constants equal to 0, then that's the end of it. All right. So you just got to kind of enjoy those moments when they happen. All right. And the other two problems, they kind of work the same way. I'll get some solutions and videos up for that. Just like I said, some of these are kind of overkill. You know, once you realize what the progression is, it's just a matter of carrying it out. And in a lot of cases, it's just writing. You know, so you know, you just got to kind of grin and bear it.